We'll move on in view of time to our next presentation, Dr. Jodie Lutkenhaus. We are now moving from vaccine development to development of smart batteries for energy storage. So Dr. Lutkenhaus is the Axalta Chair and Professor at Walker Department of Chemical Engineering at Texas A&M. Dr. Lutkenhaus was chosen for her innovation and development of redox active polymers for metal-free energy storage and smart coatings. By developing new molecular scale characterization methods, Dr. Lutkenhaus discovered fundamental connections among polymer dynamics, properties, and performance. In 2021, Dr. Lutkenhaus and her collaborator, TAMEST member Dr. Karen Woolley from A&M University demonstrated the world's first degradable peptide batteries. So I'd like to invite Dr. Lutkenhaus to the podium for her presentation. And again, we will have a few minutes after her presentation for questions.
Hi, everyone. Thank you so much. I wanted to thank TAMEST, the O'Donnell Endowment, my husband over there and his two sons, and our two sons. Sorry. Little nervous. Thank you. I want to thank Texas A&M University and TEAS for their constant support and allowing me to realize my wildest imaginations in the lab. And I also thank my students, postdocs, and collaborators. And I also thank Mark Bartow for nominating me. So, oops, here we go. So batteries are essential to modern life. I know you all have a battery. Even if you're noodling around on your phone right now, you're using your battery. But I want you to think about, what do you do with all those devices, with all those lithium-ion batteries when you're done with them? Do you put them in your junk drawer or your electronics drawer, right? Do you throw them in the trash, which is even worse? Do you recycle them? I know you don't recycle them, because there's not really a good standardized way to recycle them. So what we're talking about right now is essentially the problem we're facing or will face in the next few years. It's going to become even more urgent as we begin to grow with electrified transportation, electrified vehicles, and electrified trucks. This is demonstrated by the future commitments by major automobile manufacturers like GM and Ford, also government commitments to electrify transportation with the US and the EU. And so therefore, the growth in batteries for electric vehicles is anticipated. But we have limited global reserves of the constituent elements that go into batteries. So eventually, we're going to hit a wall with supply and demand with lithium-ion batteries. So let's look at that even closer. Lithium-ion batteries contain three components. There's a cathode, which contains, there's a cathode that contains a lithium metal oxide. The most common one you'll see in your battery now is lithium nickel manganese oxide. There is an electrolyte, usually lithium hexafluorophosphate with non-aqueous cyclic or linear carbonates. That's kind of the source of those catastrophic fires. That's the fuel for your fire in those lithium-ion batteries. And then there's a negative electrode or anode, which is graphite or some kind of carbon-based material. So if we look at the elements that are in the lithium-ion battery, the ones that we need to be careful about in terms of supply and demand include lithium, cobalt, and nickel. A techno-economic analysis of these elements that came out last year predict that we will face cobalt and nickel shortages in the years 2035 and 2045 respectively. And this isn't even including what we're facing now with Russia's war in Ukraine. And this report says that the long-term lithium-ion battery price will be dominated by the cost of cathode materials. With Russia's war in Ukraine, there's now more uncertainty about the world's nickel supply because Russia is a large nickel supplier and refiner. And Besides that, what really personally motivates me in this topic is the well-known human rights abuses with the use of child labor in artisanal mining in the Democratic Republic of Congo for cobalt. What's really the problem that I see is that the supply chain and manufacturing is largely localized in Asia. A lot of the mining and manufacturing is done in plants or mines owned by China. So this makes me think about what would happen if we have like this microchip shortage that we're experiencing now for vehicles because the US gave up a lot of its microchip manufacturing capabilities. What will happen with batteries if we don't have a better hold on our supply chain and manufacturing? Well, one solution to that is obviously recycling. But even though batteries have been around for decades, we're still recycling only less than 5% of our lithium-ion batteries. And this is because the technology to recycle lithium-ion batteries is not well developed. It is coming, and the Department of Energy is investing huge amounts of money in recycling lithium-ion batteries. But it's still not settled the best way to do this. And furthermore, recycling lithium-ion batteries is very energy intensive. So you might feel all warm and cuddly about recycling your lithium-ion battery, but you might, at the end of the day, be emitting more carbon dioxide than you really wanted to. So that makes me think about what the battery of the future will be. So the battery of the future would contain materials that are easily domestically sourced with low CO2 emissions, something like biomass. It could be manufactured and recycled in the same location, so kind of along the lines of distributed chemical manufacturing. It would perform the same or better than today's status quo. And if we could achieve all of that, then we could enable any country to source, manufacture, and recycle their own batteries where they want, when they want. And so that could democratize energy storage and kind of open up the supply chain for more economies to participate. Now, my original training is in polymer science, and my original thesis was about using solid polymer electrolytes in lithium-ion batteries. But when I started my career, I didn't want to do ion conduction anymore. I wanted to do something different. So I thought, I'll study polymer electrodes for batteries because there's a lot more action there. There's actually a reaction happening there. So I was really lucky to enter into that field before it became much more popular. So I thought, how about this idea of organic batteries? It can address a lot of these issues, but as you'll see in a few slides, the performance isn't quite there yet. An organic battery would replace the positive and negative electrodes with organic molecules that are redox active. They could be small molecules, but in my lab, they're macromolecules or polymers. The electrolyte could be the same electrolyte that we're already using, or it could be a sodium-based electrolyte, magnesium-based electrolyte, or even organic electrolyte if you want to go metal-free. Okay, so without any numbers, you think, wow, this sounds really great. Why don't I have this already? Well, there's major problems in the energy and the cycle life of an organic battery versus a lithium-ion battery. I can point out certain molecules that get you this extraordinary capacity, energy, and cycle life, but there's always another problem around the corner. And that's really where the exciting research is to be done. Now, one of the things that's most exciting about organic batteries is that they have this exceptional power. So power is what allows your car to go from 0 to 60 in a few seconds. It's what allows you to recharge your battery in the span of time that it would normally take to fill up your gas tank. Now, if you have an electric vehicle now, you know it takes hours to really fill up that battery with charge, but with organic batteries, it can just take minutes. So the landscape for organic energy storage is that we need to address certain challenges, namely the capacity. So if we're designing a molecule for this battery, it should have low molar mass, it should be capable of multi-electron transfer, you should fully utilize its redox activity. The energy should be improved, and energy is capacity times cell voltage. So for that to work, you need to have organic molecules that are stable on the positive side and the negative side. They can be useful in highly oxidizing and highly reducing environments. Ideally, they could be compatible with sodium or magnesium, some earth-abundant elements, so we could get away with lithium. Or if you wanted to go metal-free, they should be compatible with organic electrolytes. Now, I'm going to tell you a little bit about some of the science we've done that's gotten me up here on this stage. And it has to do with one of my favorite molecules called PTMA. This is kind of the star of this larger class of radical-containing polymers, which are some of the most promising types of materials for organic batteries. So PTMA is this polymer here. It has an aliphatic backbone, which means it's a hydrocarbon, and then its pendant group is a tempo group that has a stable nitroxide radical. So we can synthesize this polymer in our lab any which way we like, and it's quite water stable, temperature stable, air stable, so it's really tolerant to a chemical engineer like me. And we can oxidize it and reduce it reversibly by exchanging an anion, any type of anion you like. Meanwhile, you're exchanging these electrons, which is how you store charge. The redox potential of this polymer is 3.6 volts versus lithium, so it's just a little bit lower than that of your lithium-ion battery. Its theoretical capacity is 111 milliamp hours per gram, which is, again, a little bit lower than your lithium-ion battery, but we can get really close to this theoretical value. And then this molecule in particular has a very high cycle life and fast charge and discharge. So this is just showing you can charge it in minutes and still get acceptable performance. Now, when I entered into this field and began to study these molecules, my first question was, how do these things work? Because you see there's a radical on there, that's an unpaired electron. That's crazy. That should normally be really highly reactive. But with the conformation of this group and these 4 methyl groups, it's sterically stabilizing the molecule. So there's something unique about this molecule that allows it to operate the way it does and to do it reversibly. So if we want to understand how the ions and electrons move in this polymer, we need a way to jump down into the molecular level and observe how each and every ion and electron moves. Our approach is to use a technique called electrochemical quartz crystal microbalance with dissipation monitoring. We didn't invent the technique, but we've invented and developed a lot of the extensive data analyses that go into analyzing where everything is. So as an example for this talk, I'll just give you one example with PTMA and its anion triflate. So instead of X, it's a triflate. If you transfer or store 1 coulomb of electrons or charge, the mass of the electrode should change by 1.54 milligrams. So if I can weigh that, and I can compare if I get higher or lower, I can tell you if solvent molecules are moving, I can tell you if cations are moving, I can deconvolute what is moving when at a certain state of charge. So here's the principle of QCMD. It works based on a piezoelectric quartz crystal. So if you have a watch, not a Fitbit like I have, but if you have like a regular watch, you have this piezoelectric quartz crystal on you right now. A battery, your watch battery applies a certain voltage to it, and it has a resonant frequency at which it vibrates. Now, imagine you add a mass onto that crystal, like an electrode. It's going to vibrate at a different resonant frequency. And then if I can open up my battery and split it into all the different pieces, and I only look at this one electrode on the quartz crystal, as I oxidize it and reduce it, as mass comes in and out, I can observe the change in the frequency. And then using viscoelastic modeling, I can then tell you on the nanogram scale what the mass is. And then I can begin to tell you about how this polymer works. So this is some example data that we got for this polymer PTMA. It's in a lithium triflate electrolyte, so we still have lithium there, but we don't have cobalt or nickel, so we're doing a bit better. And to study the way it works, we apply a triangular voltage wave here. So we charge it and discharge it. Meanwhile, we get peaks and valleys and current. That's commensurate with storing and releasing charge. And we see with our QCMD data, just pay attention to frequency here, we see step changes upon oxidation and reduction, step changes up and down. So qualitatively, we know mass is going in and out, corresponding to exactly these peaks and valleys with the current. This is the same data, but we're plotting it, instead of in the time domain, we're plotting it with the voltage. And we've applied a viscoelastic model to estimate the solvated mass of the electrode as it's being charged and discharged. So as we go from a low voltage to a high voltage, we have PTMA take up an anion into, so that PTMA can be in its oxidized form, the oxoammonium cation. So at that same voltage at which we see those peaks and valleys, we see an increase in mass of the electrode because the anion is being injected into the electrode. Now, that's just the beginning of the analysis that we do in my lab. We certainly don't have time to go through all of it. But from this analysis, we can decouple how many solvent molecules are traveling with each ion. We can decouple the lithium cations, the anions that are moving. We can even decouple the time scale of it into millihertz resolution. This is just one example of the sort of analysis we can do. We have the mass of the electrode, and we're plotting against the charge as we're oxidizing it. So we start here where it's just PTMA, and we begin to oxidize it. And what we see is that the mass actually decreases. And at that time, it was totally unexpected. We spent 18 months looking at that graph, trying to explain what it meant. And we finally, after a lot of thinking and studying the literature, realized the only explanation for how lithium ions could be participating in this reaction is if the polymer electrode itself is swollen with electrolyte. So when we have these organic batteries, we have to think of the polymer as a sponge or as a gel soaked with electrolyte. There's cations and anions in there, and so both of them are participating. So at early states of charge, an anion comes in to balance that first oxoammonium cation, and for charge neutrality, a lithium cation has to leave, so the mass goes down. And then after that process is finished at higher states of charge, the anion comes in to further complete the reaction, balancing other oxoammonium cations that are generated. So from this knowledge, we've continued this study with many other systems. We've kind of defined a principle or an operating principle for these polymers, which is swelling of the polymer electrode is beneficial to enhance kinetics and performance. It allows you to charge and discharge the organic battery faster. It improves the cycle life, and it also improves the stability and the capacity. Okay, so in the last part of my talk, I want to switch gears. I took you down to the molecular level. I want to bring you up to a larger level where we're thinking about that ultimate battery that we could recycle. Maybe it's domestically sourced, or at least from renewable materials. So together with Karen Woolley, we asked the question, how might we achieve a circular battery life cycle? And we're not going to start with a lithium-ion battery. We're going to start with molecules themselves that could be sourced from biomass, from life, or from fossil fuels. In this case, Karen Woolley helped us develop a polypeptide chemistry where we start with amino acids, and Karen Woolley's group synthesizes them into polypeptides and then attaches on redox active groups so that we can generate cathode and anode materials to make a polypeptide redox active battery. My group assembles the battery, characterizes the battery, and then when we're finished with the battery, you can add an acid to sort of digest or chew up the polypeptide, and the battery degrades on command into amino acids and its original starting products. So in principle, if we could take all those digestion products and separate them out, then we could reconstitute them into the second generation battery, and so on. But I'll tell you right now, we could only get as far as degradation because the separation is very challenging. All right, so here's a schematic of what that battery looks like. So we have a polypeptide backbone, and on the positive electrode side, we have these polypeptides with the tempo groups hanging off, these little stars decorating it. So those tempo groups, those are the same type of chemical reactive groups you saw with PTMA. And then on the negative electrode side, we're using a Viologen group. Now I know Viologen isn't the best choice, and we're looking at other options as we speak. If you're really interested in the chemical structure, these are the really exquisite polymers that Karen Woolley's group synthesized for us. You can see the polypeptide backbone, and then on the anode or negative electrode side, the Viologen group, and on the cathode side, we have these tempo groups hanging off. And what my group did was we assembled those into a battery. It was a metal-free battery. We're using organic electrolyte. And we analyzed the full cell behavior. This is a cyclical tamogram where you see peaks originating from both the tempo and the Viologen groups. We charged and discharged the battery. We're getting a capacity around 30 milliamp hours per gram. For an organic battery, it's okay for a full cell battery. Compared to a lithium-ion battery, it's only a fifth of the capacity of a lithium-ion battery. So you can see there's immense research opportunity to improve our performance. As we charge and discharge the battery, the capacity fades. And this is really one of the key challenges I told you about with organic batteries, cycle life. Now, in this case, we identified the problem as the material dissolving, not a problem, because we can then use those in a different application, such as redox flow batteries. So we have a paper now in revision where we're using the same types of molecules, but for redox flow batteries in medium in which they're fully soluble. Okay, so with parting thoughts, organic batteries offer a path forward for metal-free or domestically sourced battery manufacturing. So we can design it all the way from the molecule to the device and then back again to capturing that molecule to be used again. Recycling of organic batteries is within reach. My group is currently working on it right now, and I wish I could share those results with you in a year, but I think it's definitely possible. The major challenge for my community is to improve the capacity and energy so that they can become more competitive with lithium-ion batteries. With that, I want to thank especially my husband in the audience. And I just have some photos. I'm gonna cry, so I'm just gonna stop. And our two sons, so adorbs. And then especially I want to thank the DOE and the ACS PRF who have really supported me in this multi-year journey of exploring organic batteries. And so thank you, and I really look forward to your questions.
Presentation, as a technologist working in the mobility sector, particularly in the e-mobility space, your research is really amazing, and it can be a game changer in terms of better technologies. So great work. We don't have too much time, but we can probably afford one or two short questions. Sure.
I couldn't, resist this beautiful polymer science. So I've seen that you have the tempo as the selected alkoxyamine. Have you thought about using SG1 as a polymer scientist? We know so many nitroxides you have available, and SG1 with the phosphonic ester group. Are you considering expanding the library of alkoxyamines?
Yes, thank you for the question. So the question is about expanding the library of radical groups and other redox chemistries. We are absolutely doing that. For these super fundamental studies like you saw in the first part of the talk, the tempo group is perfect because it's very well behaved. What you see is what you get. But we now want to expand it to other radical containing groups, especially the ones that are more promising, that have higher capacity, ones that can be ambipolar, or there's some that can do not necessarily radical groups, but multi-electron transfer. So we're definitely going in that direction. I've been studying tempo for 5 years. I'm a little tired of it, honestly.
One more. Does it matter the molecular weight of polymetacrylate? Because at the larger molecular weight, you're going to carry more tempo. Do you study the influence of the molecular weight of the polymer?
The question is about the molecular weight of the polymer. I personally haven't. Other people have. Once you get above a certain molecular weight, the polymers are all entangled and it doesn't really matter as much. But the key thing, if you're in this area, is if your molecular weight is too low, your electrode dissolves as you're using it. And so if the molecular weight is high, it won't dissolve. And so I would always say higher molecular weight is better.
Okay, thank you.
Thank you.